Welcome, welcome, everybody. A few words of warning here. This is all my own work, so it's all my IP, so it's free for you to use. So don't worry about IP issues with all the code that you see, etc. Despite the fact that you may see some similar code in banks, if you ever work there. That's my company, Count Zero Limited. I'm a gun for hire, a contractor. Okay, a quick outline. We all know C++ is used because it makes it fast, yes? The point is in high frequency and low latency trading, we want to get an order to the market as fast as possible. It's basically memcopy from an input socket to an output socket with a little bit of twiddling in between. The answer, obviously C++ and good hardware, come on, really? That's why we're here, C++, yes? We've seen lots of nice features mentioned, if const expr and so forth. Const expr has also been introduced in the past. So, I'm going to look at the effect of the compiler, because we've heard in the fishbowl things like modules. Modules are going to be a panacea, aren't they, for performance? Again, concepts could improve performance as well, and so forth. Really? Performance quirks in compiler versions, how fast they generate code, and also the quality of the generated code. I won't be able to go through all of these examples, so I could either have a straw poll of which one you'd like to see, or I could choose myself. And given that I work in merchant banks, I'm going to choose myself and impose my decision on you, because I've never had the opportunity to impose my decision on so many people, the power. Then what we're going to do, what I will stick with, is this putting it all together, this fixed emit bit translator. Okay, a little bit of terminology for you. In the financial markets, there's something called FIX. It's a ASCII-based pair value protocol, so you've got a name value pairs, and it's awful. It's very slow. There's lots of conversion of doubles to double strings to double values, and so forth, backwards, forwards. Then we're going to look at different compilers, take a little bit of a break, because we've all been talking, well, why not just you compile with a different compiler? Surely that's going to be easy. Yeah. No, it isn't. We'll have a look at that. And then we've all heard about this thing called Spectre and Meltdown. Well, what about the impact of the hardware? Which do we get the most bang for our buck? All the hard work in micro-optimizing C++, which I love doing, as you'll see. Change of operating system. Common law is the operating system is about 2 to 5% of the runtime. Is it? What about changing the hardware? We're going to then have a look at the results. So there'll be lots of graphs, lots of details. I'm going to skip through this pretty quickly. HFT and low latency trading, performance critical. The point is that if somebody places an order with me and I put it to the market faster than someone else, I get all the business. Most of this is all basically through algorithmic trading. And what is algorithmic trading? Well, there's different types of algorithmic trading, but the basic type is what you've got is computer programs that check market situations, place orders, and hopefully you'll actually be able to have a fill on the order. Most of the orders that are sent to the market are cancelled. It's about a 10,000 to 10,000 to 1 ratio between place an order, modify, 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 cancel, or place an order, modify, modify, fill. And the fill is what you want, because that's what gets you the money. But this is also micro-trading. So I'm Boohis, one of the people who enables flash crashes and various things like that. Most of the trading done on the stock markets today, about 80% to 90% is this stuff, automated algorithmic trading. Only about 10% of it is meat sacks, or traders, as they like to be called. So, faster is better. Right, it's not rocket science. We're not safety critical, okay? It's not airplanes, it's not rockets, it's not nuclear reactors, it's not missiles. To be truly fast is to do nothing. So the best way to get better performance is tell your boss, no. How about whiz-bang feature? No. You've heard of Yagni? This is extreme Yagni. It's message passing. We want low-level control because clearly we want to do things like ISOL CPU, NUMA control. We want to look at the PCI bus. We perhaps want 2 PCI buses on 2 processors with separate memory buses, etc., etc. Okay, we know C++ can be relatively low level. I'll skip through this so we can look at more interesting things. But also, it's nice and high level. The point is complex abstractions can be modeled easily. But most importantly, I can hide behind a facade some really gnarly micro-optimizations. We've also got increasingly capable libraries like Boost, Frozen. Frozen is a very interesting library. What it is it's a const expra unordered map. This is very, very handy for implementing things like meta-state machines. So if I get an order coming in, what do I translate that to? Normally, the obvious one is an order going out. But if I get a fill coming back, sometimes I'm supposed to put an order acknowledge, then the fill. And meta-state machines can allow me to implement that much more easily and clearly. But obviously, I want my meta-state machine to go as fast as possible. Sadly, the details of that are interesting and ongoing. I'm going to ignore other languages that might be better suited to this, like D or functional Java. Basically, garbage collection kills performance, and what they do in banks is they turn off garbage collection and they wrap everything. They write C in Java. So you've got, I don't know the full details, but basically you just use the low-level bytes and fiddle with that, and don't do anything in Java itself. Is there much more to it? I mean, I've said it sounds very simple, but I've mentioned the devil is in the detail. We look at hardware. Lots of money is spent on hardware. Remember, we're evil. We don't care about the climate. So what happens is everything hot spins. And you turn off all C states. You turn up the power to max on your processor. You don't let the BIOS the processor slow down. And because the latency in terms of the processor speeding up again, it kills you. And also, you've got multiple processors, bus per processor, as I said, and you dedicate them to tasks. Network infrastructure, you make sure it's co-located. What does co-location mean? You've got exchanges, your computers are next to the exchange. Little known fact, you've got 6-foot racks. The price of the rack is in proportion to the height, and the middle of the rack is the really expensive part because average cable length is shorter. And that means you're faster to the market. Yes, they are worried about microseconds. They are worried about nanoseconds. I've worked with people who worked on trading systems where it was 500 nanoseconds. But that's in hardware. Software issues. Anything in this area will confound you. From people deciding, that's a nice bit of high bandwidth network, let's use a bit of it to surf the web, which has happened. The person got fired. Also, operating systems. Not all distributions are created equal. Some have better tool sets, some have better support facilities, some have better facilities for coding. CentOS is an excellent example. It's very primitive in its tool set to maintain and support and investigate bugs. By the way, you may find that I will hate CentOS throughout this talk. It's commonly used in banks. Why? IT infrastructure people, the DevOps guys, sadly, not that bright. Configuration is very important. Things like ISOL CPU, C groups for more modern people. ISOL CPU is used a lot because 2.6 series kernels are still used. Why, I don't know. Not all compilers, indeed, as we'll discover, are created equal, which is faster, pardon me. Clang, GC++ or ICC. I don't have ICC because I'm doing this at home, so I'm paying for it myself. And this is done as a hobby, so whenever I do this, I'm not working and it costs me a lot of money. So I'm going to focus on GCC, G++, and Clang with C++14 and 17, C++14 and 17, some versions of Clang and ICC. Okay, hardware. Hardware is very, very important. You need to know the hardware in this area. This is an old AMD bulldozer, as you can see, relatively old. But what's nice about it is, A, you can get hold of the processor architecture diagram like this, whereas usually these are fairly restricted because it's quite confidential where things like branch predictors go, width of instruction fetch, how many decoders you've got, and so forth. But the very, very important issue here is we've got two L1 data caches, which are only 16K in size, whereas our L1 instruction cache is 64K in size. Another very important feature of this is the number of ALUs we've got, AGU address generation units. Address generation units are really important because, of course, we fetch stuff from memory. All those references, they're pointers. LSU load store unit. So I will hark back to the arrangement of the bus and the optimization techniques that I use, driven by what particular hardware I have in my processor. Okay. We've all heard about I've talked about hardware and processors. We've seen the branch predictor up at the top, which is, well, as we've heard of Spectrum Meltdown that came out last year, and various derivatives of Spectre. Again, I'm not going to read through all this. All these slides are available. You can look at it. The basic point is that one is very basically an issue to do with branch prediction. The other one is very roughly to do with speculative execution and prefetching things into the cache. And how might they impact performance when you have to mitigate against these in your hardware? Okay. I'm going to look at a few case studies. In particular, performance quirks in compiler versions. Really? Compiler versions? Different quirks? Surely not. Surely a compiler is, after a while, remember GCC4, GCC5, 6, 7, 8 now, surely it's all been well done, well proven, nothing changes, stuff just gets a bit better. Perhaps. Well, we'll see. I'm going to stick with the first version as a warm-up, and then what I'll probably do is go straight through to the curious case of memcopy. Okay, here is some very complicated code. Why is it complicated? It shouldn't be. It should be really obvious. Static const, and the static is there because it's internal linkage, and therefore, what ideally should occur is we know that 0, that string, should actually be just written in the docx section to dest. There should be no opcodes anywhere. That's the ideal. Why am I interested in strings? Remember I mentioned fixed messages. Fixed messages are strings. And I'm comparing strings, matching strings, converting strings. So this is important for string comparisons. If we look at GCC 447, by the way, you might think this is ancient, nobody ever uses it. There are at least 3 major merchant banks on the street that account for roughly 7 billion a day turnover that use GCC 447. So it is financially probably the most important compiler in the world. All the rest are down the tail. Now, we can see here in 447, you see those 2 move abseeks up there, scheduled together? That's a problem. Because the issue rate of move abseek on this old architecture, that AMD architecture I showed you has a curious quirk. The vector unit is extremely slow. So therefore, it should have been, the second one should have been shuffled down. But the nice thing is we can see immediates in there. Those immediates go into the instruction cache. Remember the instruction cache? 64K. Data cache, 16K. The instruction cache, sorry, the data caches are a vital commodity. that need to be preciously conserved for what's really and truly important. Another little known fact is the instruction cache takes 1 clock cycle to fetch that. The data cache takes 10. So if we move things into the data cache here in 473, notice string is now no longer an immediate, it's on the stack. So it has to be fetched from main memory into the data cache, L3, L2, L1, then into the registers, and the instructions performed. This is dramatically slower. Hang on. This is memcopy. How long's memcopy been around for? 40 years? 50 years? Surely they would have just got this right by now. And this is really basic stuff. Okay, those are old compilers. What about newer ones? Crikey. 481 to 63, it's gone back to using immediates. And it's scheduled the move abseek better. We can see in 7 series compiler, by the way, all of this is courtesy of Godbolt. All hail Master Godbolt. We notice here VEX instructions are being used, so this is even more efficient. But the problem is we can't use immediates with VEX instructions. So although the VEX instructions might be faster, we've taken a potentially 10 clock cycle hit. So is that really better? Is the -MAVX a good idea or not? GCC 8, again, we see a difference in code generation. The very, very important point is this. It's a very unstable output. If it was just one output but bad, I can work with that. The problem is it keeps changing. I can't rely on it. Okay, surely Intel, right? They've been around a bit. They've got a Bob or 3. Surely they can manage to generate this code reliably and efficiently. Well, no. Notice the 2 vmove UPSs up there, badly scheduled. They're next to each other. Notice also immediates aren't used. There's no immediate instruction for the VEX instruction set, but surely Intel would have worked that out by now. That frankly, they could have used a slower instruction, but used immediates because the instruction cache is big enough. ICC 18, again, different instructions. Clang does a reasonable job, but the problem is it's still using the stack. It's still using data cache. Okay, does this really matter? You're going to see a lot of graphs. Notice it's a log scale. Notice also we do have error bars on here. The error bars, I use mean average deviation rather than standard deviation. And it's a better measure for these sorts of results statistically. The error bars are within 2%. These are run millions of times, the tests, to get a stable, reliable result with a good expectation value. What I did is I created my own small string optimized string. Why? There's a mountain, I'll climb it. The interesting fact is I then dropped in different versions of memcopy. And we can see here, we've got the small string. This is a test case. We just create a small string with a small string with a string literal, a small string literal, and construct it, destroy it. Here, a big string. So in other words, it's got to allocate on the heap and call delete. So obviously, it's all slower. What's interesting is there's the deviation. Look at the different versions of compilers. There's a significant difference in performance. Hang on, 10 to the 16. What's the clock cycle of my processor? Gigahertz. 10 to the 9. What's happened is that's been optimized out. I'm just measuring the difference in time between timestamp, timestamp. So what's happened is we can see in this code, certain test cases can be optimized out. Remember I said doing nothing is to be truly fast. What I want is I want to be up there in the 10 to the 16 case. I want my code to be optimized out because my compiler has been enabled to get rid of as much as possible. Forget about even using the instruction cache. If I can do nothing, that's even better. So all those test cases, all those if conditions, if I can make them disappear, that's good. So what's this showing is that in certain instances, when one crafts one's code, we can actually get rid of unnecessary string operations. This is nice. For example, an assignment, it's been removed. But the point is, it's unreliable. Notice GCC 6.3 couldn't do it. But GCC 5 could optimize out the code. Hang on. So what we're saying is different versions of GCC apply const expr differently and unreliably. Yes, I know const expr can be evaluated at compile time in a const expr evaluation context, recursive definition, but the problem here is it's unreliable. Clang follows a similar model. But what's very interesting is here, the big string replace. Notice how Clang 5 significantly, that's a log scale, remember, significantly outperforms all the other compilers, including Clang 6. Our compiler performance is utterly unreliable. Now, this one, static branch prediction, use and abuse. All these slides are available. I've submitted them to conference organizers. You will get this full set. Because of time, I'm going to have to go through an abbreviated version. So I'm going to skip this example, if you'll forgive me. And there are a number of details. Okay. I think the switch one is an interesting one. A lot of people seem to think in common law that either the first case label or the default are the statically predicted fall-throughs. Remember, we've got built-in expect. But built-in expect these days doesn't generate any operand prefixes, and if it does generate the prefixes for the jumps, they're ignored in modern architectures. But it does affect the way code is generated. The point is that in fact, that's not so at all. I spent some time looking in GCC and raised a bug report in GCC about their documentation, because the implementation of their switch statements is actually very, very interesting. It's essentially you get cliques of lookup tables. And to search between the cliques, one uses a balanced binary tree. Sorry, a binary search. And the case labels are ordered to put them into cliques. So essentially a depth first, a balanced binary, crikey. A binary search occurs to find the correct case label. This is handy because instead of having 10 if statements for 10 case labels, one can have log 2 of 10. You can have about 3 or 4 lookups, jumps instead, which is much faster. But there's no static prediction. The default or the first case label are not statically predicted. They're not put high up in the code sequence with one jump to check. Why are jumps important? Jumps are important because on superscalar architectures, there's something, we have a number, we have a surfeit of pipelines in which we can then execute predicted code. So if I have if A, else, I can execute the if and the else, and what I can do is quash the result depending upon the condition. The problem is if I've mispredicted, then what happens is I need to roll back and start from the other case statement. the other branch. The problem with starting from the other branch is if I've got enough resources, I'll execute both branches. But that's rarely the case. Usually I don't have enough resources, so I'm only executing one, so I have to roll back. And if I have to roll back, that's about a 20 clock cycle hit. And that's a lot of time. So I want to reduce the number of jumps. Now we can see here, remember I said we've got this rather curious binary search that occurs. So if we look at this and we see the labels, L3, L4, L5, hang on, there's L2. See how that's dropped in? L7, another L2, L2, L7, L5, L3. Notice how they're out of order. If you squint a little harder and you look at the bar 3 and then the bar 5, 6, 4, 1, 2, you can sort of see that there's some kind of perverse search operation occurring. Of course, assembly is not so easy to look at, so it's less obvious. Bizarrely, Clang does make use of built-in expect to hoist the statically predicted, pardon me, to hoist the statically predicted branch from the case labels so that then we've got fewer jumps. Because if I want to say, if L4 is the case statement that has been selected by the switch, then what we've got to do is we've got to see the JEL3 at the top, JGL4, we've got 2 jumps. Whereas if I was, say, the, let's say, L3, I want to choose one that's a long one. Where's L1? So if we want to go bar 1 over there, which is L5, we've got 3. L2 is 4 tests, 4 jumps. And these jumps, the more jumps we've got, the less likely we are, on average, to be able to accurately predict it. Because if my predictor is 90% accurate, then that's 0.9 to the power of 4, which is getting very close to 50-50. 50-50 means I've got a 50% chance of it being, which one was it, bar 1 or not, which means I've got a 50% chance of a rollback, 50% chance of a 20 clock cycle hit. This is very important to me. Okay. You might think, well, why don't I just do if bar 1, which was the 4th case, I'll hoist it out, I'll make it, put an if statement in there, and then an else, and then I'll put my switch statement in. The problem is as I've already mentioned in a previous example I didn't have time to show you, sorry about that, is that the compilers will not respect that as a static prediction. And what they might do is they might flip the else around and presume that the else is the statically predicted branch. By the way, GCC is quite exciting. Look at the result. Take some time, if you do, and have a look at the slides here, because GCC, in general, will fall through to the else, static predicted, apart from newer versions of GCC, when it's the other way around. All other compilers presume it's the if. Processor architecture designers presume it's the if. Take it from me, the people in GCC got it wrong. And I do hope there's a GCC dev here who can shout at me, because I'll shout back, because I've actually raised a bug about this, report about it. And what's interesting is it actually turns out nobody knows why GCC does it that way. Old Fred wrote the code, and there's a probability, and the probability is 1 minus 0.6. And they don't know why it's 1 minus 0.6. Why is there the 1 minus? Why is it not just 0.6? Because in fact, at the optimization level, it changes from 0.6 to 1 minus 0.6. It just drops in. Why? They don't know. The guy left. Gave up. I'm not surprised. Okay. I'm heading towards the meat of this. We've all heard of C++. We've heard comments regarding firing the most competent developer because what he does is he writes code that's completely and utterly awful and nobody can work out how it works. Me, I'm that man. I did it. This is code I've got at home. Don't worry, I would never even dream of using this at work unless there was a clearly obvious reason why to use it. Angle brackets, let nobody tell you otherwise. Angle brackets are good. It's a good drug. Just do it in private. What we have here is a template function called memcopyopt. And what I've got is it takes two strings, source and destination, and what it does is it goes to an immense amount of effort to try and generate an optimized sequence of code, assembly instructions, to do it in the fewest assembly instructions. It doesn't necessarily respect scheduling, but it presumes that the compiler isn't so stupid as to not be able to schedule this sequence of assembly instructions. Okay, that's a bit of an assumption, as we've already seen with the earlier example of memcopy, but we'll live with that for the moment. And what we've got is this horrible thing called a line unroller. And notice the types here, M256i. Yes, these are AVX, SSE, etc. types. And then what we do is we make use of a little lambda here, Mr. Lambda. Don't you like it? This is generating assembly, and I'm using templating and lambdas to do this assignment. Yeah, I've had to cut out a lot of the code. This is about 1,000 lines of code, so you really, really don't want to try and debug it. Do it a little bit at a time, and do write the test cases to make sure that your initialization and termination conditions for doing the copy is done correctly. Yeah, oops, there was an error there earlier. I'm actually quite proud of that in a way. In a bad way. Okay, so what assembly does it generate? This insanity. Excellent, look at it. The most incredible template bit of programming. Well, not incredible, there are harder stuff. Tie. Okay, the big problem is look, I might have generated the nice VEX instructions for doing the move using AVX2. This is all very nice. The problem is the howler. It's using the stack. But newer versions of GCC have managed to actually put the char string immediate into the instruction cache. Excellent. Bizarrely, the tail has not been. So it's actually chopped it into two pieces. And what's interesting as well is notice the VEX instruction has to use the stack, but move abseek can use an immediate. So what it's done is, whilst the load is occurring from main memory or the data cache for the string, the move abseek is executing. Remember, this is my old AMD chip that has a bizarrely slow vector unit. And the VEX instructions are bizarrely slow. So this is actually a good idea, it doing that. Okay. What about Clang? At least it's stable. It's done something similar, at least it's stable. So, judicious use of template metaprogramming appears to have given us a rather interesting memcopy result, at least in terms of the assembler. Of course, it's notoriously hard on superscalar chips to work out exactly how many clock cycles this takes, because it depends on the issue rate of the instruction, it depends on what else is in there, is in the pipeline, it depends on hazards, it depends on whether the data's in the instruction it already fetched into the data cache, maybe it's in registered. Remember, a superscalar chip doesn't just have the registers you can see. It has architectural registers that are hidden, and the data might actually be in those. So it doesn't have to do a load from the data cache if it's already there, depending upon register pressure and so forth. So it's notoriously hard. The best thing to do is have a look at another compiler, because it's there. Again, the problem here we see is that the Intel compiler, I'm not trying to knock Intel. What I'm trying to say is that different compilers get different results, and they can be bizarrely unstable. So expect the unexpected is what I'm trying to say here. We can see that the ICC 13, it's got a rather slow, apparently, looking set of move Qs and move Ls, because it's actually broken up the instructions that I was supposed to emit. And it's actually the compiler, the optimizer, has actually changed it into separate instructions because the optimizer thinks I can actually run two move Ls at the same time. And what I can do is use the move DQs, the vex instructions, but the move Qs can then be scheduled immediately after to hide latencies. Whereas in ICC 16, there's quite clearly a different performance model used inside the compiler. Why? Nobody knows. Unexpected things can occur. Okay, does all this matter? The performance test is all. I'm a great believer in measure, 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 and measure again. And what I did is I used my same small string optimized string, which had a mem copy in it, but no longer has it got standard mem copy. I dropped in this. So if I've got a char literal, my optimized mem copy knows the size of the array and therefore can emit the optimum set, in some sense, optimum set of instructions to do the copy. Okay, again, notice these aren't log scale. Notice how small string replace, the dramatic difference in performance. Notice also how standard memcopy goes so much faster. Sometimes a lot of effort can yield nothing, or worse. But also notice the next graph with Clang. Notice how my optimized memcopy is suddenly much faster in the assign, the small string assignment. How odd. And yet the small string replace, Clang is equally baffled by even its own memcopy. Notice also how, see that 10 to the 15, it's been optimized out. That's where we want to be. Okay. Compiler versions and performance. Here you can see GCC from 4.7.3 up to 8.1. We can see Clang versions from 3.8 to 6. And the various performance differences for my small string optimized string, standard string, and we can see the ABI changes here. And there's this thing called GNU CXX vstring. Visa string is it's sometimes called, which is a small string optimized string that existed long before the ABI change for standard string. Notice one, how unbelievably variable the results are from the compiler versions. Notice how GCC 5.3, notice here, this is with ABI 11, without ABI 11. Same compiler, different ABI. Notice the dramatically different performance we get from my small string optimized string, where it could be optimized out at the top. Notice this is a log scale. It could be optimized out in the old ABI, but with the new ABI it couldn't. Why? In fact, it's in general slower everywhere. I mean, only Clang 3.8 is that bad. How did they manage it? There is very little reliability in performance. Okay, forget my string. Let's look at the green line with the X's, which is the standard string. Notice how variable that is in performance. We can see that GCC 5.1, it actually did pretty well in performance. Only 6.3 beats it. Notice how, yes, the small string optimized string has done well. But if you want a quick hit in performance, GNU CXX Visa string is faster still, uniformly faster. Notice also how very, very variable we get. You see, Clang here, it's much more reliable in performance. It also manages to optimize out more things. Whereas, if we look again at these, the amount of ability to optimize out is very significant. Okay. This is going to model, notice the stack string constructor-destructor assignment performance. The previous one was constructor and destructor performance. So we're just looking at a different set of test cases because is the performance affected by the test cases? We can see, again, a similar kind of structure where we see GNU CXX V string doing very well. We see standard string only picking up after the new ABI. We see GNU 5.3 having a serious performance issue. Again, Clang improves after 3.8. And we see GCC, the newer versions of GCC are doing reasonably well. But not as fast as the oldest version. Don't tell your boss that. If you want really fast code, use GCC 4.4.7. Don't tell your boss, because of course there's no C++11 in that. Yeah, no 14. It's back to the good old days. I work at a major merchant bank, and that is a major blocker for upgrading C++ standards, that simply the compiler can't cut it. Again, we see a similar model with replace. Replace is a harder operation, so we're less likely for the compiler to optimize it out. I'm glad to see that my sweat going into my small string optimized string, it's in general faster than the rest, apart from Clang 3.8, where I don't know what they were doing there. And again, GCC 5.3. In fact, there'll be many other companies that have reported back to GCC that their 5 series compiler, particularly 5.3, sucks in code generation. 5.2 as well, and 6.3 is usually a sweet spot. Okay. Let's look at this translator. And just catch up. What time do I finish? 15 minutes, thank you. Excellent. Okay, this is as you can easily imagine, it's heavily templated. We've got a socket that we listen to fixed messages from, these messages where I have a new order. Then what I do is I translate it to this thing called an MIT BIT variant. MIT, Millennium IT, BIT Borsa Italia. It's the Italian stock exchange. Why am I using the Italian one? B comes before L, LSE. That's why. So lexicographically in my code, it's at the top. It's equivalent. And what it is it's a special binary protocol designed for high-speed trading on the LSE. On Borsa Italia. Millennium IT produced the software for these exchanges. I've used, most people in HFT now gasp when I say I use BoostASIO and say, oh my God, that's so slow, why don't you use something else? I've not found it to be a performance issue. There are such things as open SolarFlare cards and open onload drivers. These are specialized networking cards that are ultra high performance, that can basically get they take a message off the physical socket and it's in memory in 56 clock cycles. Normally it's 256 clock cycles. They are extremely fast. I don't use those because they're also extremely expensive. And they won't loan me one, the buggers, despite saying that they would. Both Exablaze and Solarfare. I've sent a message. We've got client sends a message, translator translates it. We've got a simulated exchange, sends a response, translate it back, client receives the response. All in quotes. Oh, yes. Already said that. Computer. I've tried it with and without NUMA control. I've tried it whilst it was both busy and quiescent. I'm a Gen 2 Linux user. Even my laptop runs Gen 2 Linux. It's a highly optimized kernel and a highly optimized installation. It's old, slow computer. So that's why we see mean round trip, high is bad, low is good. We can see on this graph the lower magenta line, that's the link time. So that's the time, sorry, that's the simulated time. That's the time that my simulated exchange takes to receive a message and send a response. The graph above is the entire round trip. What I want is the entire round trip to be as low as possible. What we can see in this graph, these versions, we've got incrementing compiler versions and incrementing changes in code. So sadly, I've changed two things at once, but sometimes I retest with the same version. So here you can see, remember I was saying GCC 5 series compiler? It's very slow compared to 6. There we have it. A massive performance loss with GCC 5 compared to GCC 6. Again, I've done various code modifications. You'll have to take it from me with these various check-ins, but you can actually verify the check-ins yourself if you want pain. The general drop in improvement in performance from build 1850 to newer builds, in general, there are performance optimizations added. So we can see that my tweaks in the code with these micro-optimized mem copies and various other things have, in general, improved the code performance. But when we move to newer versions of GCC, GCC 8.1, by the way, the results for 8.2, I have not yet done them, but they're basically the same as 8.1. We can see a massive performance drop between 7.1, 7.2, 7.3, 8.1, 8.2. Why is this? One can only speculate. My speculation is that the poor GCC compiler writers, there's only so many of them, and they can either implement new stuff from the standard or optimize what was there. They're implementing new stuff from the standard. We, members of the Standards Committee, are at fault for that. That is the reason why C++ 17 is, and greater, are unlikely to be adopted in merchant banks. That performance loss. Because that is game over. You're out the market. You've gone from 60 microseconds to 80 microseconds overnight. That is a 30% performance loss. That is disastrous. Again, some of these error bars, oh, by the way, the error bars, the earlier error bars are 4%, the later error bars are 2%. The reason why is because of these big performance differences, I decided to tighten up my error bars to make sure that it wasn't a statistical anomaly. Notice different versions of ASIO. My ASIO library is horrible. It's extremely cut down, has zero flexibility, and just about works. It's unbelievably thin. There is no noticeable performance difference between it and Boost ASIO. All hats off to Mr. Koloff for that, and the other gentlemen who were involved in Boost ASIO. It's a really impressive library. Let no one tell you it's slow. Yeah, and don't bother writing your own. Okay. We can see that with judicious micro-optimizations, we can get a performance improvement, and we can see a roughly doubling of performance improvement from that graph. But what's the cost in compile time? Remember people talking to you about modules and how they'll improve compile time? I'm sorry, that's full of it. Change your compiler. This is the time taken to compile the code on my computer. It's about 40 minutes in GC 7.3 and 8.1. Similar times for older compilers. There's Clang. Just over 5 minutes. It's about just under 6 minutes. Change the compiler. Anybody who tells you that modules are going to make GCC 8 times faster, oh, you mean it'll make it go just as fast as Clang is today? Yeah? Is that rubbish? Yes. I mean, with respect to them, they're not paid programmers. They work for it as a hobby. You know, those who don't work for Red Hat or whoever. So I have a great deal of respect for what they do. But the basic point is, just improve the implementation of your compiler with what you're doing already. Forget modules. Throw it out the window. Delete it. Ignore the keyword. The only real reason for modules today is code obfuscation. That's it. Oh, and by the way, modules as well, because they won't use, because hash defines won't be supported in them, there'll be 2 phases of modules. As far as I'm aware, I believe I could be corrected on that, but I believe it won't support hash defines. That basically means the vast majority of your code can't be modularized anyway. Unless it's new code and you avoid hash defines like the plague. Yeah, getting it to compile with Clang. I don't know if any of you who have ever tried. My code base is quite old. It's about 15 to 18 years old. Well, the oldest bits are that old. There's newer bits as well, of course. It was a lot of work. One hears about libcxx because, of course, the header files for Clang versus GCC are different. And the Clang developers have put a huge amount of effort in getting their compiler to work with GCC. The GCC header files and libstandard C++. Basically, the problem is if you choose to go to libcxx, that means that if you're using something like Boost, which is installed on your system, that means you need a new local customized installation of Boost with a different ABI. Otherwise, you've got to recompile everything to use the new version of Boost that uses Clang. Oh, does everything compile on your computer for Clang? I don't think so. So I used libstandard C++. It had some issues. There's a defect report in hash table policy, which I had to hack. There's an interesting bug in Clang as well. Sometimes no except true won't pass. P-A-R-S-E. So you just have to delete the true bit, and then it works. Okay, need to skip on a bit. The error messages are horrendous, as usual, as you might imagine. Now, I mentioned about operating systems. What's the impact of that? Well, I'm going to cut the results quickly. We see CentOS, Xubuntu, and Gentoo. The Gentoo is a cut-down installation. We can see there is a dramatic difference in impact from the operating system alone. Look at that. See the CentOS 6.9? Over 90 microseconds. Lower is better. Gentoo, or Xubuntu, it's just over 20 microseconds. Yeah, really. Over 4 times performance difference. Remember, I sweated over years to get a doubling of improvement by micro-optimizing. By simply changing the operating system, I can get a 4 times improvement. Really? Let that sink in. Consider what you're doing. What is your operating system? It's extremely important. Let no one tell you it's between 2 to 5% until you've measured it yourself. Okay, what about hardware? My old AMD versus a heavily overclocked Intel iCore 7, which was 3 years ago, it was the bee's knees. Nowadays, it's pretty passé. But the point is, we can see here, again, roughly a 4 times performance improvement. The last thing we should be doing is worrying about the performance of our C++ code until we get our operating system sorted, until we get our architecture supported. Because, what? 3 years of effort in micro-optimizing. How much did that cost? Hundreds of thousands of pounds. The operating systems are free. Changing the hardware, a few £1,000s. It is not worth it, micro-optimizing. Unless you want to do it, look elsewhere. I mentioned Spectre and Meltdown. We can see that Spectre and Meltdown the mitigations have a major impact on performance. These figures have been checked by Intel. I actually spent 3 hours on the phone talking to Intel because they saw these results and they got a bit worried and wanted to call me up. And I was grilled by 3 chaps from Intel, and they said, yeah, this is basically what we see as well. We can see different kernel versions are impacted in a different way. So you really do need to think, if you're in a performance area, do you need the mitigations, A, and B, how might they affect you? Here's a big graph of all the versions of Xubuntu. The takeaway is the low latency kernel for Xubuntu is rubbish in this instance, for this test. Just use the generic one. Gen 2 pre and post mitigations, also a major impact. The key point again is don't presume anything. You must test and test. And if somebody tells you, oh, it won't have any effect, the first thing one should do is disbelieve them. The next thing one should do is ask them to produce the figures. Third thing to do is ask them what's the error bars. Fourth thing, then maybe believe them. And that equally goes for you listening to me in this talk. Go away and satisfy yourselves that it affects you with your test cases. We can see that it's clear it's a very complicated situation. Different versions of compilers play poorly with different architectures. In fact, I've got cases where I have architecture-specific micro-optimizations, where some work better on AMD, others work better on Intel. The Folly library. Andrei Alexandrescu commonly talks about double to string conversions in there, integer string conversions. He has various versions of doing it. And on Intel, they have one performance profile. On AMD, a different performance profile. One needs to select the hardware very wisely. As you've seen, the operating system is crucial as well. More details, the impacts of the loss and percentages and so forth. Again, there are issues surrounding the city. The city is in a highly regulated area, and that means we have legal requirements for applying mitigations, and if we don't, we need to go to the lawyers at the bank and ask them for permission to not do it, because sometimes we could be found personally liable if we make a poor choice, unless we have seen to approach the lawyers and make a best effort. This can affect other industries as well. Discard Amdahl's law at your peril. Often I start this talk, but because of time, I presume you've all run Valgrind against your code. And I presume you've all run Valgrind call graph against your code. So you can identify the 90% of the 10% of your code that's taking 90% of the time. Because don't do this until you have done that. Always avoid micro-optimizations because of the huge technical debt. The choice of the operating system should never, ever, ever be underestimated. I very much hope these slides have proved that to you. If they haven't, please reread the slides or talk to me later. Preferably with a beer in hand. Beer. More information? Please feel free to ask. I also have all the links are active, and I've got plenty of links at the end to all the papers and so forth that I've referenced in the talk. Ladies and gentlemen, thank you very much for your time. I hope you've had a great conference. I certainly have.
Thank you, Jason.
This whole thing has been very interesting, but I've seen, so actually we have 4 unknowns here. First, the hardware, the operating system, the compiler, and the language itself.
Correct.
What I don't understand why these big banks, we know they have billions or whatever, why don't they use more, I don't know, real-time stuff? Like one thing that I can think of is real-time operating systems. And if that is not enough, they can even use FPGAs, because I know companies that are doing computer simulation on FPGAs, and those actually means running your logic in real time. And with today's hardware, you can really scale your algorithm as much as you like on an FPGAs. And then if that is not enough, you can scale horizontally, and yeah, you can also have, I don't know, distributed computing, whatever you can think of. Because, yeah, of course, this probably translates in huge costs implementing and maintaining, but probably in London, there is no limit.
I think there's excellent points raised. The language issue as well is obviously, one can imagine later versions of my code use newer features from C++. So hence things like context, etc. have been used, and we see those anomalies in performance, or I like to call them nice bits in performance. The points you raise about the banks has exercised my mind a lot. FPGAs are used, yes. Custom operating systems, no. Why? Curiously, banks are perversely cheap, and they love using things that are free, even if it's rubbish. Why? Because the people who make the decisions in using those are not the people who have to use them. So it's very easy for a big boss somewhere to say, hey, they're going to use this because it saves this much money on my bottom line, without actually thinking of the ramifications. In terms of FPGAs, and this affects both operating system and compiler version, or compiler choice. This is, as I said, these are to some extent sweeping statements, a little broad. FPGAs, you make a very good point. I've met FPGA developers, and they're really interesting, and I mean that in a good way. They're a very interesting breed. They're very different to programmers. And they don't like the, how do I put it technically, the shit that goes on in the cities. And they choose to move elsewhere and work elsewhere in better environments where they don't get shouted at. I can't tell you a little story about an FPGA program that had an interesting quirk for legal issues, but beer gives plausible deniability. Remember I mentioned flash crashes? Anyway, I need beer for plausible deniability. The point is that there's a lot of pressure, and these guys can earn equivalent money, similar money, in doing games, in doing mobile phones, whatever requires embedded stuff. So the problem with FPGAs is it's A, hard, and B, there's very few developers who are a certain type, and they don't fit well with banks. Whereas I'm a programmer, I like lots of money to pay for my holidays, beer, champagne, my wife, etc. And therefore, I'm happy to prostitute myself to banks in exchange for money. And there's a standard aphorism at banks: the more you get paid, the more shit you deal with. The higher the salary, the worse the code. And I've never seen this aphorism fail. So I'm sorry to say, it's a bit roundabout, but basically it's to do with the corporate inertia, legacy code, and the people who make the decisions are not impacted by the decisions they've made. And and there's probably other factors, so there's no one simple factor. As ever, there's always a compound of issues. Oh, by the way, I have worked at Morgan Stanley, where Bjorn Strustrup also works. Again, I'm happy to make non-career limiting comments on that later. Oh, one of my bits of code, the trading system you saw up there, there's a very similar trading system that trades called NXT Gateway that trades for Instanet. That runs in production to this day. There's no C++ programmers employed in the UK to support it and maintain it. I wrote part of it, got it into production, and it trades something like 3 billion a day turnover. There's, as far as I'm aware, never been a day's outage. The point is that micro-optimized code can be very reliable if you've got the test cases.
So write those test cases, right?
Rock on!